All right. So thank you very much for the introduction. First, a few words about myself. I studied electrical engineering. I got my bachelor's degree from DHBW Stuttgart. At the time, I was also working on the first prototype of the telephone I'm going to present here. Then, for my master's and PhD, I went to Munich and focused more, as the Herald said, on embedded security. I had some side channel attack projects, and now, professionally speaking, I'm working as a penetration tester. If you want to reach me, you can do so by email or on Mastodon. At first, I would like to say thank you to some people without the help of whom the project would not have been possible. First, Fine, he helped me with the ringing voltage generator as well as SMB soldering. Then Heke, he helped me find a flaw in the ringing voltage generator. Then Telekom Historic Bochum operates a quite awesome telephony museum in Bochum that I visited. So if you're in Bochum, I highly recommend you to go there. Deal Queen, thank you for taking pictures and helping with the presentation. And HiOZ for your phone I could use for last-minute oscilloscope shots. And then, Tall Guy, I think he was here in last Congress. He had a Wandfernsprecher project that I took also as inspiration. RF guy Hans Gelke, he gave me also ideas. And there are a couple of other people, for example, who donated the phones of their grandparents to me. So thanks to everyone. Let me begin about the planar telephony system in general. First about the infrastructure. So we're talking about a system that has been there since like the 1920s in the very early stages up until 1980s, 1990s. So on the left you see so-called main distribution frames, or in German Hauptverteiler. They contain the electromechanical or electronic components that connect the lines together. Then in the middle you have the primary connection points, or Kabelverzweiger, and they're basically serving as just a passive wiring between MDF and NTP. Then NTP is the network termination point, or in German Abschlusspunkt Linientechnik. That's basically there in the basement of each house, and that's connected to the user socket where your phone is connected to. The funny thing is, or the interesting thing is, when you had local calls, meaning no long-distance calls, back in the old days, you really had a real electrical connection between two parties in a call, and not just voice being forwarded. Okay. So here you see a simplified circuit diagram of FeTAp phones. On the left you see the so-called ringer. So that's the bell that rings when you receive a call. Then GU stands for Gabelumschalter in German, or in English it's hook switch. And when you lift up the handle, it connects the line here and closes the loop here. And then NSI and NSA are two contacts of the so-called Nummernschalter or Wählscheibe. In English it's called a rotary dial. And NSA is called Nummernschalter Arbeitskontakt in German, or off-normal contact in English, and it's closed when you operate the rotary dial. NSI is the impulse contact, or dial pulse contact, that generates the impulses. I'll show that later on. Okay. Now for the ringer. Basically, this is an excerpt from the German telephony standard 1TR110/1. And if you want the ringer to ring, you have to apply an AC voltage between 32 volts and 75 volts with a frequency of 25 hertz. Down below, you see a screenshot from the Fritz box. I didn't have access to any real telecom equipment, so I used that. And I hope you can see it well. The frequency is quite well, but the ringing voltage, it's 37 volts at Fritz box. It's more on the lower end of the specified range. And this telephone in particular also didn't ring very loudly. So I took that as into consideration when designing the circuit I'm going to show. Okay, now we can receive calls, and we want to dial as well. Therefore, Impulswahlverfahren, or pulse dialing, was the classical way of dialing, and that basically means you make short interruptions that are called pulses, where basically the loop current goes down to 0, and then in between these pulses you get pauses, and the loop current goes up again. I also measured that on Fritzbox. Here on the left you basically see the dial tone, that's this wiggling here. I measured that with a series resistor to measure the current. So this is the current being shown here. Then you see 3 times the current going down, 1, 2, and 3. So this means I dialed the number 3 in the rotary dial. And yeah, just to double check whether we're in the specifications, the pulse duration is 59 milliseconds. Pulse duration is 59 milliseconds here. That's within the specification. And the total duration, it says 98 milliseconds. That's also within this range here. So that works. Now I've shown a video here, or I'm going to show a video. So please take a look how the NSA closes, so the off-normal contact closes when the user operates the rotary dial and opens up only at the very end. And also take a look at NSI, the dial pulse contact that repeatedly opens up to generate the pulses. So now NSA is closed. Now it's turning back. Now you see 1, 2, 3 times NSI opened up again, and at the end NSA opens up again. All right. So now we have a call established. What happens then? Then we're only interested in the right part. Basically, you see a DC current needs to be going through the microphone, 20 milliamps minimum when a call is active. And just one word about these microphones. Microphone is this circuit symbol here. It's typically carbon microphones, meaning that there are carbon granules inside that have a variable resistance that is modulated by sound. And yeah, the microphone modulates the loop current. And basically, in the very basic circuit, you could also connect the loudspeaker. That is, let's see, that is up here in series. But that would mean that you would hear yourself very loud, and you want to avoid that. So therefore, this transformer has been introduced, so that the AC part, basically one part goes to the right, one part goes to the left, and in theory, the signal coming from the own microphone would cancel out itself. In practice, it's just attenuated, so you still hear yourself, but not as loud as if it wasn't that circuit. Okay. So we already know a lot about telephones itself. The other funny or interesting thing to know is how are the connections made. They're done by using so-called rotary dialers. They basically typically connect one line to 1 out of 10 by 10 connections. And whenever there's one pulse, the dialer makes one step. There are older systems like System 22 in Germany or Strauger, who is the inventor of automatic dialing. They first move vertically, and then for the first pulse burst, and then they move horizontally for the second burst. And in newer systems, newer means like from 1955 or so, System 55, they use a so-called EMD, Edelmetall-Motordrehwähler in German. So they have stepper motors inside, and they only move horizontally. First, they make 10-step increments, then 1-step increments. And let me show a video here again. Oops. So you see I dial the number 5 here. You see it goes up, the dialer goes up 5 times, and then it turns right. Why does it turn right? Because it has to select the next free dialer in the next dialing stage. That's what often happens. So first making steps always represents the digit you have dialed. Second may also represent the digit you have dialed, or it may represent that the next dialing stage, the next free dialer has to be selected. Okay, let's move on. The FeTAp 61. FeTAp stands for Fernsprechtischapparat or desk telephone. There's also FeWAP, the Fernsprechwandapparat for wall phones. And usually you see the name FeTAp 611, which is the very basic model, but there are also models that have more features like a ground key or so-called A2 circuits that allows to connect multiple telephones in series. And yeah, the phone itself was manufactured by different manufacturers like DTW, SEL, or Siemens, but the design and the contract comes from Deutsche Post. It was introduced in the 60s, and colorized variants have been introduced in the early 70s. And I think that also has made it become some kind of cult classic. Okay. Now let's go to the FeTAp Unplugged, so the modification I'm going to present. At first, let me mention that I'm not the first one or the only one who was working on that. There are a couple of publications. This is only a short list. For example, the FeTAp 611 modification by Björn W. posted on microcontroller.net. He used an old Nokia 5110. I can show that here. So that was from 2007. Then it was improved by Delta Golf 7 X-Ray Oscar, who used the Siemens C25 and industrially manufactured a circuit board. I can show that here as well. Then Justine Haupt, she made, I think, even a complete mechanical design for rotary cell phones. And then, the other project was the GSM Wandfernsprecher from Tall Guy. So that all, oops, sorry, it was too fast. And then, my project has some history as well. 25C3, I took my first prototype with me. That was still made on perf board. It used a Siemens S35 with 80 commands to dial. Let's see, this thing here is a transformer that is operated inversely, like a normal power supply transformer, to generate the ringing voltage. So, I mean, everything worked and it was quite nice, but I wouldn't want to give that away as a present to people who are not in tech or don't want to tinker around with such things. And this is why I chose to make a version 2. So for version 2, my goal was to be independent from network technology. So don't want to be outdated when, for example, 4G or 3G gets outdated. I also want to make switching between using the FeTAp phone and the normal cell phone simple. Then battery charging was missing. I wanted to add that too. The big issue also was the ringing voltage generation. As you saw, that was a little improvised last time, so I wanted to make that better. And most importantly, I wanted to use standard components. Okay, so for connectivity, I was thinking firstly about a 4G or 5G module, but eventually I chose Bluetooth and chose to make it, technically speaking, a Bluetooth headset rather than an actual telephone, because that would prevent me from switching SIM cards, or prevent the need from switching SIM cards when I wanted to use the actual phone. The hands-free profile covers all required use cases, so you can just use it as a regular phone. And the funny thing is, you also can have non-standard use cases, like you can use it as an MS Teams headphone, or you can make WhatsApp calls. So that's, I would say it's even better by that. Then the last choice was which module to use. First, I was thinking about microchip, but they require a proprietary Windows configuration software, and the evaluation board is quite expensive. So I went for Physicom as a module supplier and Qualcomm as a chip supplier. I think there are other chip suppliers or other module suppliers using Qualcomm chips as well. Okay, so back then the most challenging part was the ringing voltage generation. The phone operates on a single lithium-ion battery cell. So we have an input voltage of between 3 volts and 4.2 volts. The output voltage shall be between 32 and 75 volts, as said. Ideally on the more towards the upper range. So the idea was to use a switching mode power supply for generating a high DC voltage, and then an H-bridge for AC generation. All right, so the circuit that you see is, or the circuit idea is called flyback converter. Basically, the good thing is you have a transformer here, and the voltage scales up with the turns ratio of the transformer. So I used a 1:10 turns ratio transformer, and that was quite well. And these type of converters are also used for high voltage applications, like in camera flashes, or if you're familiar with electromagnetic fault injection and the chip shouter, that also uses this kind of circuit design. Basically, you have an input current that's going in here, and that's basically controlled by this MOSFET. And whenever the current is switched off here, the magnetic field in the transformer dissolves itself through the secondary loop, through the output current, and charges this capacitor here. How does it work? There's this controller chip. I chose one from LT or analog devices because they have a pretty good simulation library. And basically it measures both the current flowing through the primary loop as well as the voltage that is output. And then it generates these gate pulses here. Okay, I did have a small problem when I designed the circuit first. So this screen is basically a screenshot from LT-SPICE, the simulator, where here everything looks quite perfect. So the target voltage is reached within 15 milliseconds. That's awesome. Problem was, in practice, it was never the case. So you see, basically here, there's a very steep slope, as it's supposed to be. And then it starts, ending up somewhere at 40 volts, but not at 60 or 80 volts that I actually intended to be. And you see some sort of wiggling here as well. So that apparently was a problem. And by reading the data sheet, I found out that there is a mechanism that is called current fault detection. And when that happens, basically there's a capacitor that is charged for ramping up the SMPS, sorry. And so what basically happened is what's written in there. It's an auto retry hiccup mode. So this is the voltage measured at the soft start pin. So here the soft start capacitor starts to charge, and it's supposed to go up all the way and then reach the final voltage. But what happened is here there is an overcurrent fault triggered. And so it goes down again, then it starts charging again, but here another overcurrent fault is triggered. So basically we're in this loop, in this hiccup mode, and I didn't get out of it. And it took me some while to figure out what happened. My first assumption was electromagnetic interference problems, but that turned out not to be the case. The problem was, and I found that out only by reading data sheets of other manufacturers, that a too fast soft start time that is defined by the value of this capacitor here that destabilizes the current control loop. So the controller tries to increase the current too fast, and then there's overcurrent protection triggered. Okay, so after fixing that, basically the voltage ramp up looks like this. So there's a ramp up time of 55 milliseconds. So now we have a stable high DC voltage that we can use. How do we make an AC voltage out of it? The concept or the idea is called H-bridge, and the goal is to generate a DC voltage with twice the amplitude of the DC voltage. So AC voltage twice the amplitude of the DC voltage by toggling the transistors that are switched on. So first, for example, you switch on this one and this one, and then turn around, switch on this one and this one. And this way we can generate a simple square wave. That was the first, I would say, step of improvement. However, I wanted to make a more smooth movement of the clapper so the hammer doesn't smash against the bell and then stops. I wanted to move more smoothly, and therefore I wanted to create a sine-shaped ringer current. How did I do that? So here that's traced from a logic analyzer, and you can see here this alternating between on and off states is still the same for the upper transistors, for the P transistors. But for the lower transistors, for the NMOS transistors to the bottom, I did something else. I feed in a higher frequency PWM signal with a duty cycle that is modulated by a sine half wave. So you can see it here. I hope it's visible well. So here you see the end of one half wave and the beginning of the second half wave. And the only thing you're supposed to see here is that the duty cycle, so the width of the pulses, starts very narrow and then gets wider and wider. And this is basically a sine wave that is modulated, or that modulates the duty cycle. All right. So when we look at the ringing voltage that is generated out of this, it honestly looks quite ugly. Technically speaking, from the measurement perspective, the AC voltage is quite high, 60 volts RMS, and the frequency is also well, but the voltage itself looks ugly. But what's important, or more important, is the current. And so this also measured against a shunt resistor here, and this is basically not perfectly sign shaped, but very good enough. And most importantly, the bell or the ringer rings quite loudly with that approach. Okay, next challenge was to have a dial tone. Obviously, if you want to have a classical phone, you want to have a dial tone as well. The microcontrollers that I used, or the microcontroller I used, is an STM32L4. Is pretty well equipped with digital to analog converters. So I used that. And I used a voltage divider and a potentiometer here to scale that down. So I use a full-scale sine wave that I'm generating to reduce quantization noise, and I'm generating a 425 hertz sine wave. That's basically according to the standard as well. Then I use a voltage divider and a voltage follower as an amplifier, and then I basically use an audio switch chip from Texas Instruments. Or you can use any audio switch chip to switch the audio between the dial tone and the Bluetooth module when you actually have a call. All right. So this is pretty simple. You want to read in the rotary the number you're dialing. You can use microcontroller GPIO pins for that. That's pretty simple. Use a pull-up resistor externally. I configured the microcontroller pins to be pulled down. And one thing to note is the capacitors here. They are just used for debouncing. Okay. Then one thing that is, I would say, not really tricky, but you have to know it or you have to keep it in mind, is the carbon microphone. Basically, it's just a variable resistor, so you cannot just connect it to the input of a phone, or of a Bluetooth module, because the Bluetooth module wouldn't supply it with a current. So what I did is connect it in series with a current measurement resistor here, and then basically have an RC element and feed that into the line-in of the Bluetooth module. So this way, you basically measure the current and feed that in current through the microphone and feed that into the Bluetooth module, and that works pretty well. Okay, so now the state machine of the phone, that's basically implemented in C. Currently, I'm planning to use Rust, but the hardware support was not well enough there, I would say, for the platform I used. So you start in the idle state, and from the idle state you can go to power saving mode by the ARM Cortex M4. That's called stop mode. And then basically I think many of the transitions are pretty obvious. I would mention or highlight two. One is Bluetooth not connected, because obviously you can lift up the handle when there is actually no connection. And then you should get a congestion tone, or in German it would call it Gassenbesetzton. That would be the same as if in the classical phone network, no free dialing. There's no free dialing stage at a certain point. And the other thing that is not as obvious is you can obviously create or make a call from your actual phone and not from the FeTAp. So when you lift up the handle, it can be that there is already a call established. So you want to make sure that you pick up that and not show the dial tone again. Okay, then charging. That was also, interesting to know. There are different standards. One is called battery charging 1.2, BC 1.2. The other one is over Type-C charging. They're pretty simple. They're using resistor encoding, meaning that both the source, the power supply, and the sink, the telephone, have resistors in there. And both the resistors create a voltage divider, and then the sink needs to measure the voltage created by the voltage divider and decide how much current it can draw. And there are integrated circuits for that. A couple of them. I use one by Monolithic Power Systems, and that works quite smoothly. And another improvement would have been to use power delivery, where basically there's this chip or chips would talk to the PC and negotiate another voltage or higher currents than 3 amps. But that's, I would say, not necessary for this single cell charging. Okay, last, I would say, challenge I was facing is, since version 2 shall be really pretty, I actually wanted to use the original connectors, not improvise too much. And these connectors and the hook switch as well, they're not produced anymore, so I desoldered them from the actual old PCBs. And here you see one peculiarity. You see like a cascaded pin outline, and basically the thicker part shall be pressed into a hole and remain in the hole, as you see here, and the thinner part is supposed to be soldered. And in the first prototype, the hole diameter, which I didn't take care of too much, was too small, so it didn't really fit in well. So I made a test series with different hole diameters, and now basically the connectors fit in very well. Okay, now we're pretty much done. So let's assemble all the pieces. This is how the prototype looks like in KiCad as a model. And then when you manufacture it and solder it, it looks like this. And the cables are debugging cables. They're no longer needed anymore. And you can assemble that or put that together into the housing here. That's this phone here. It's fed by a lithium-ion 18650 battery. And then you can put it all together and have a phone that looks like normal, but you can use it on the train, for example, as well. So that's about it for the technical side. There are some interesting social aspects with this project too. As said, once I had a train breakdown in Spain, everyone was annoyed, and then once I put out my phone, made a call, and then everyone was super curious and totally forgot about that they had been annoyed. So that was quite fun. Or once I was at a flea market and had this phone with me, and people were just thinking maybe, I don't know, this guy bought this phone on the flea market there. But then it started ringing, and then everyone was like, "Oh, can I try? What is going on here?" so they wanted to make calls as well, and yeah. And the most funny thing was at work. At one point, my normal headset malfunctioned, so I connected the FeMAP to Teams, and I had a video call. So the colleagues were thinking I was like making fun of them, and yeah. Especially when you have a call with upper management, that's quite funny. So yeah. Yeah, so to summarize, I think it's a curious conclusion that this project accomplishes in an unexpected way what actually the phone was historically designed for, namely to make people talk to each other more. Okay, so that's about it from my side. You can always reach me by email, or I've set up a little webpage where you can find details as well. Thank you very much.
Wow. Thank you for that awesome talk, Michael. We do have some time for questions. Please line up at the microphones. We have 6 of them in the hall. If you're online, again, we do accept questions from the internet on hackint.org in 39C3-hall-0. That's not the number, but it's the letters. And we already have a couple of questions. Microphone 1, please.
Thank you for this talk. I'd like to ask, how is the Bluetooth pairing and unpairing and connection stuff handled?
That's pretty simple. You can configure it to be pairable when it's not paired, and so basically, just whenever it's not paired, you can pair it, or any phone can pair itself.
Well, once it's paired, how do you pair it to a different device?
You can either send AT commands to unpair it. That's currently not implemented. There is a button that can be used for that purpose.
Okay. So you added a button.
Yeah.
Okay. Mm-hmm. Thank you.
Okay.
Do we have a question from the internet?
At this point, we have no questions from the internet.
Okay, then let's carry on with microphone 1.
Thank you very much for your talk. I was wondering if this system would be hard to implement in other phones, because obviously I'm Swiss and I don't have like the marvelous German one. I've got the Swiss one, which is pretty much the same, I guess, but would it be hard to re-implement that? Because I think the system is roughly the same. So did you release this the design somewhere?
Yeah, I'm planning to release the design. It's not done yet, but please check out the webpage.
Thank you very much.
It'll take a couple of weeks, hopefully not too long. And yeah, the schematic is supposed to be generic, but obviously the layout needs to be adapted. Yeah.
Okay. Perhaps a practical question. Did you find a affordable source for dynamic capsules? Because these charcoal-based ones are very noisy, to my experience, especially if they get old.
Yeah, I know. So for now, I've just bought telephones on eBay and some replacement parts on eBay. And for some telephones, they already have transistor-based microphones, or like modern microphones with a electronic circuitry inside there that can be used as a drop-in replacement. And I think there are some replacement manufacturers as well that you can use. Yeah.
Microphone 2, please.
Thank you, and thanks for the talk. Actually, I have one of these old phones. I got it at a flea market several years ago, but didn't get to make it work. I'm planning on doing something similar, but without disassembling the phone, just to add something and use the old plug. Mm-hmm. When you provide the schematics on your site, will you also provide the exact values of like the capacitors and resistors, or do I have to like figure it out on myself?
I mean, when I'm publishing it, I want to publish it so you can definitely reuse it. But you can also come to me later on. I'm going to the MUC3, the Munich CCC assembly, and we can talk there.
All right, thank you.
Mic 1, please.
Hi, thanks. What about the rotary dial? Do you have any like additional functionality for if you're listening to your podcast, like to like go 10 seconds back, like the multimedia functionality that you have on other Bluetooth headsets?
Not yet, but that would be pretty practical. So yeah, there are some things on this to-do list as well. Yeah.
Okay, just a question. You did the heavy lifting of doing this everything manual for the line interface, for instance, generating the ring voltages and currents by hand because you like the electronic design, or why didn't you choose one of these existing FXO chips which do everything in one and you just set up the right TR protocol?
That's a good question. In the first place, yes, that was meant as a learning effect, or to see how to design things on my own. Yeah. On the other hand, I think the availability on JLC PCB was also, I would say, limiting. Yeah, I think that's about it for now. And these chips that I know, they don't operate on 3 volts. They operate maybe on 12 volts. And
no, there are. If you look in modern ones, in modern gateways like you find from big telecom operators, they operate totally on 3.3.
Oh, okay.
Then everything, and they really do 90-volt ringing voltage and all this crazy stuff.
Oh, then we should definitely talk. Yeah. Thank you.
So there are no more questions in the hall. I think there is still no question from the internet. In that case, let us thank Michael for this awesome talk. Please.